When most people hear organic chemistry, they think of something hard, scary, or totally disconnected from real life. But here's the truth. Organic chemistry is the chemistry of life, as well as materials, energy, and medicine. Everything from fuels, plastics, and fabrics to pharmaceuticals, food, and DNA is built on organic molecules. Now, the goal of today's lecture is not mastery. It's learning the language and pattern that organic chemistry uses. By the end of today, you won't be experts, but you will be able to look at an organic structure and say, hey, I know what that is, how it's built, and what it tends to do. So before we get into naming molecules and drawing structures, we need to start with a really important question. What do we mean when we say organic chemistry? Because despite the name, organic chemistry is not about organic foods or things grown naturally. In chemistry, the word organic has a very specific meaning. In chemistry, organic compounds are compounds that contain carbon, and more specifically, carbon bonded to hydrogen. Carbon is a unique element because it can form 4 bonds. That ability allows carbon to build long chains, branches, and rings. This flexibility is what allows organic molecules to be complex, and that complexity is what makes life possible. Most organic compounds also contain elements like oxygen, nitrogen, sulfur, or phosphorus, but the key feature is the presence of carbon-hydrogen bonds. Examples of organic compounds include carbohydrates, proteins, lipids, DNA, hormones, and many medications. If a compound is part of the human body or something designed to interact with the human body, there's a very high chance it is organic. In contrast, inorganic compounds generally do not contain carbon-hydrogen bonds. These compounds are often simpler in structure and include things like water, salts, acids, bases, metals, and ions. Some common examples of inorganic compounds you already know well are water, sodium chloride, calcium ions, and hydrochloric acid. Even though these compounds are called inorganic, they are absolutely essential for life. For example, electrolytes such as sodium, potassium, calcium, and chloride are all inorganic. IV fluids are mostly inorganic chemistry. Blood pH regulation, oxygen transport, and nerve signaling all rely heavily on inorganic compounds. So while this course focuses on organic chemistry, it's important to recognize that both organic and inorganic chemistry work together in the human body. Here's an important detail that often causes confusion. Not all compounds that contain carbon are considered organic. For example, carbon dioxide, carbon monoxide, and carbonate are all compounds that are classified as inorganic. While these compounds do contain carbon, they do not contain the carbon-hydrogen bond, which is why they are not considered organic. So when deciding whether something is organic or inorganic, the key idea is not just carbon, it's carbon bonded to hydrogen. So to summarize, organic compounds contain carbon bonded to hydrogen and make up the chemistry of life and medicine. Inorganic compounds generally do not contain carbon-hydrogen bonds and include water, salts, metals, and ions that support essential physiological processes. This course focuses on organic chemistry because understanding organic molecules helps us understand how nutrients are processed, how drugs work, and how small changes in molecular structure can lead to big changes in biological activity. I also want to be clear about something. You are not training to become an organic chemist. You are learning enough organic chemistry to understand how chemistry applies to human health. That means focusing on patterns, concepts, and applications, not memorizing every reaction or detail. So to review the differences between organic and inorganic molecules, let's turn to our Pearson assignment and work questions 1 and 2 from Chapter 12's in-class assignment. Pause this lecture video and come back when you're ready. Now that we understand what makes a compound organic, the next step is learning how chemists represent these compounds. That brings us to hydrocarbons, or molecules made only of carbon and hydrogen, and how we name and draw them. Let's start with carbon itself. Carbon wants to form 4 covalent bonds. This is the single most important rule you need to remember for organic chemistry. Carbon achieves 4 bonds by sharing electrons with other atoms, most commonly hydrogen and other carbon atoms. This ability allows carbon to create chains, branches, and rings, which gives organic chemistry its incredible structural diversity. Hydrocarbons are organic compounds made up of only 2 elements, carbon and hydrogen. There are no oxygen or nitrogen atoms present, and while hydrocarbons themselves are not usually found alone in the human body, they do often form the backbone of more complex biological molecules such as fats and hormones. Hydrocarbons can be classified as either saturated or unsaturated. A saturated hydrocarbon contains only single bonds between the carbon atoms within the chain, meaning each carbon has the maximum number of hydrogen atoms attached to it, hence the term saturation. It's saturated by hydrogen. An unsaturated hydrocarbon contains at least one double or triple bond between the carbon atoms, resulting in fewer hydrogen atoms, hence unsaturated. In this section, the focus is on saturated hydrocarbons, which are called alkanes. The simplest alkane is methane. Methane contains 1 carbon atom. Since carbon wants 4 bonds, it forms 4 single bonds with 4 hydrogen atoms, giving methane the molecular formula of CH4. Methane is a useful example for introducing how chemists model molecules because there are several different ways to represent the same compound. Chemists use different molecular models depending on what information they want to emphasize. A space-filling model shows the relative sizes of atoms and how they pack together in 3-dimensional space. A ball and stick model represents atoms as spheres and bonds as sticks, making it easier to see their molecular geometry. The wedge and dash model shows us a 3-dimensional model on 2 dimensions in which the solid lines are atoms in the same plane. The solid wedge are atoms that are coming out of the plane, and the dash wedge are atoms that are going back behind the plane. If you need a review of the wedge dash model, go back to last semester when we were talking about VSEPR theory and molecular geometry, and focus on the tetrahedron because this is the main molecular geometry structure that carbon atoms are taking on in saturated compounds. We also have the expanded structural formula that shows every atom and every bond explicitly in 2-dimensional space, and then the condensed structural formula, which groups atoms together to make the structure easier to write and read. For methane, the condensed formula is simply CH4. Ethane is the next simplest alkane and contains 2 carbon atoms. Each carbon still forms 4 bonds. The 2 carbon atoms are bonded to each other by a single bond, and the remaining bonds are filled by hydrogen atoms, giving ethane the molecular formula of C2H6. Ethane demonstrates that carbon atoms can bond to each other to form chains, which is one of the defining features of organic chemistry. Alkanes, as I mentioned, are saturated hydrocarbons that contain only single bonds. They follow the general molecular formula of CnH2n plus 2, and each alkane name ends in the suffix ane or ane. As the number of carbon atoms increase, the prefix changes and the molecules become larger and more complex. So for example, if we only have 1 carbon, we're going to use the prefix meth and the ending ane. For 2 carbons, it would be ethane, 3 carbons propane, 4 carbons butane, so on and so forth. Butane is an example of an alkane with 4 carbon atoms. The prefix but indicates 4 carbons, and the ane ending tells us that it is a saturated hydrocarbon, meaning we only have single bonds. Butane has a molecular formula of C4H10. When drawing butane, the most important requirement is that each carbon atom forms 4 bonds. A nice quick representation that I haven't shown yet is the line angle drawing that you can see here at the bottom of your screen. Line angle drawings are especially helpful here because they allow us to represent carbon chains quickly and clearly. In line angle drawings, carbon atoms are not written explicitly. Instead, each line, endpoint, or bend represents a carbon atom, and hydrogen atoms attached to the carbon are implied rather than shown. So this type of drawing becomes especially useful as molecules get larger. So up to this point, we have been looking at straight chain alkanes, where the carbon atoms from a single continuous chain. However, carbon chains can also be branched. When this happens, the molecule is called a branched alkane. Branched alkanes have the same molecular formula as their straight chain counterparts, but a different arrangement of atoms. For example, butane can exist as a straight chain structure or as a branched structure called isobutane. Both have the molecular formula of C4H10, but their atoms are connected differently. These different arrangements are called structural isomers. When naming branched alkanes, the longest continuous carbon chain is identified first. This chain gives the base name of the molecule. Any additional carbon atoms attached to this chain are called substituents. Substituents are named and assigned numbers based on their position along the parent chain. While the full set of naming rules can look intimidating at first, they follow a consistent and logical pattern. Branched alkanes are important because even small changes in structure can lead to different physical and biological properties. And this idea becomes especially important later on when we discuss biologically active molecules and medications. So for example, if we were going to name this branched out chain first, again, our first step is to identify our longest parent chain. And so there's two potential chains we could identify here. We could go this way, where it'd be 1, 2, 3, 4, 5, 6 carbons. We could go this way with 1, 2, 3, 4, or we can go this way, 1, 2, 3, 4, 5, 6, 7. So since this position gives us our longest continuous chain, we would say that our parent chain then is hep for 7 and then tane for all single bonds. So this would be heptane right here. Now to include this substituent that is 1 carbon, we would call that methyl. And then we would number it again to give us the lower order number. So we would number from this way, 1, 2, 3. So we would call it 3-methyl heptane. And if this is a little confusing, it's okay, guys. We're going to get practice in our workshop this week on naming lots of different molecules that have branches and cyclic and double bonds and triple bonds and single bonds. So don't panic. We're just introducing the language, introducing the patterns, introducing the rules right now, and we will get hands-on in our workshop. So as I mentioned, carbon chains can also form rings. When alkanes form rings, they are called cycloalkanes. The prefix cyclo indicates that the molecule is cyclic. For example, cyclobutane is a 4-carbon ring, and even though the molecule forms a ring instead of a chain, each carbon atom still forms 4 bonds. No matter how hydrocarbons are represented, either using space-filling models, ball and stick models, expanded structural formulas, condensed formulas, or line angle drawings, the same bonding rules apply. Carbon forms 4 covalent bonds and hydrogens form 1. So now that we discussed how to draw and name alkanes, let's review on Mastering Chemistry by working questions 3 and 4. Feel free to work in pairs, and again, pause this video and come back to the lecture when you're done. So now that we know how to draw and name alkanes, let's talk about their properties. Understanding these properties helps explain how alkanes behave physically and chemically, and why they're useful as fuels and as structural components of more complex molecules. Alkanes are nonpolar molecules. And this is because the difference in the electronegativity between the carbon and the hydrogen atom is very small, so electrons are shared relatively evenly. As a result, alkanes do not have partial charges and do not interact strongly with polar substances like water. Because alkanes are nonpolar, they are insoluble in water, and this is why oil and water do not mix. Alkanes will dissolve in other nonpolar substances, but they generally do not dissolve in aqueous-based solutions. And this concept is important in biology and medicine, where solubility affects how substances move throughout the body. Another important property of alkanes is their physical state, which depends primarily on the size of the molecule. Small alkanes, such as methane, ethane, and propane, are gases at room temperature. Medium-sized alkanes are liquids, and very large alkanes are solids. As the number of carbon atoms increases, the molecules experience stronger intermolecular forces through van der Waals interactions or London dispersion forces, which raises their boiling points. Alkanes are also relatively unreactive compared to other organic compounds. Because they contain only single carbon-carbon and carbon-hydrogen bonds, they are considered chemically stable. Despite being relatively unreactive, alkanes do undergo one very important chemical reaction, combustion. In a combustion reaction, an alkane reacts with oxygen to produce carbon dioxide, water, and energy. And this is why alkanes are commonly used as fuels. Natural gas, gasoline, and many heating fuels are comprised primarily of alkanes. In a combustion reaction, if you recall from last semester, the carbon atoms in the alkane are converted to carbon dioxide and the oxygen atoms are converted to water in the presence of oxygen. These reactions release a large amount of energy, which can be used for heating, cooking, and powering engines. From a health perspective, it's important to recognize that while alkanes themselves are not very reactive inside the body, their combustion products and derivatives can have significant environmental and health impacts. Understanding their basic properties helps build a foundation for later discussions about more reactive organic molecules. So to summarize, alkanes are nonpolar, insoluble in water, relatively unreactive, and their physical state depends on their molecular size. Their most important chemical reaction is combustion, which releases energy and produces carbon dioxide and water. So let's take a moment and review how to balance a combustion reaction. Recall, this is a skill we practiced last semester in 101. If you need to, go back and review how to balance chemical reactions first, and then come back to this lecture. So pause and come back when you're ready. Now that we've discussed alkanes, we can move on to alkenes. Alkenes are unsaturated hydrocarbons that contain at least one carbon-carbon double bond. The presence of this double bond changes both the structure and the chemical behavior of the molecule. In an alkene, the double bond consists of two shared pairs of electrons between two carbon atoms. Because of this, each carbon involved in the double bond can only form two additional single bonds instead of three. This means alkanes will have fewer hydrogen atoms than alkanes with the same number of carbons. So therefore, alkenes follow a general molecular formula of CnH2n, or twice as many hydrogens as carbons. And their names end in the suffix -ene. For example, ethene, which contains two carbon atoms and one double bond, while propene contains three carbon atoms and one double bond. One important structural feature of alkenes is that carbon-carbon double bond is rigid. Unlike single bonds, which can rotate freely, double bonds cannot rotate without breaking the bond. This lack of rotation leads to different spatial arrangements of atoms around the double bond. This brings us to cis-trans isomers. Cis and trans isomers have the same molecular formula and the same connectivity of atoms, but they differ in how the groups are arranged in space around the double bond. In a cis alkene, the similar or larger groups attached to the double bonded carbons are on the same side of the double bond. In a trans alkene, those groups are on opposite sides of the double bond. Even though cis and trans isomers contain the same atoms, their shapes are different, which can lead to different physical and biological properties. A classic example is butene. Cis-2-butene has both methyl groups on the same side of the double bond, while trans-2-butene has the methyl groups on opposite sides. These two molecules are isomers, but they are not identical and they behave differently. When naming alkenes, the position of the double bond must be specified. The carbon chain is numbered so that the double bond receives the lowest possible number. The cis or trans designation is then placed in front of the alkene name to describe the geometry of the double bond. For example, cis-2-butene and trans-2-butene have the same base name, butene, but the cis or trans prefix tells us how the molecule is arranged in space. This naming distinction is important because different isomers can have different melting points, boiling points, and biological effects. From a health and biological perspective, cis and trans differences are especially important in biological systems. Molecular shape matters. Even small changes in geometry can affect how a molecule interacts with enzymes, receptors, or cell membranes. Later in the course, we'll see examples where the shape of a molecule determines whether it is beneficial, harmful, or inactive. So to summarize, alkenes are unsaturated hydrocarbons that contain carbon-carbon double bonds. These double bonds restrict rotation, leading to cis-trans isomers. Cis and trans alkenes have the same molecular formula, but different spatial arrangements, and these differences are reflected in their names and properties. Let's see if you can correctly identify whether a molecule has a cis-trans isomer or not by working question 6 in Mastering Chemistry. Pause and come back when you're ready. One of the most important chemical behaviors of alkenes is that they can undergo addition reactions. Addition reactions occur because of the presence of the carbon-carbon double bond. The double bond contains a region of high electron density, which makes it more reactive than single bonds. In an addition reaction, atoms are added across the double bond. The double bond breaks and a new single bond forms. As a result, the alkene product becomes a more saturated molecule, the alkane. These reactions are important because they explain how unsaturated molecules can be chemically modified. A useful way to think about addition reactions is that the double bond acts like a point of entry where new atoms can attach. Different addition reactions involve adding atoms, different atoms or groups across that double bond. One common and important addition reaction is hydrogenation. In hydrogenation, hydrogen atoms are added across the carbon-carbon double bond through the form of dihydrogen. Each carbon in the double bond gains one hydrogen atom, converting the alkene into an alkane. Hydrogenation is widely used in both industrial and biological contexts. A familiar example is the hydrogenation of oils. Many plant oils contain unsaturated fatty acids which have carbon-carbon double bonds. When these oils undergo hydrogenation, hydrogen atoms are added to the double bonds, making the molecules more saturated. As fatty acids become more saturated, they become more solid at room temperature. And this is why hydrogenated oils are often more solid than unsaturated oils. This process has been used to create products like margarine and shortening. However, partial hydrogenation can lead to the formation of trans fats, which have been associated with negative health effects. This highlights how changes at the molecular level can have significant impacts on human health. Another important addition reaction is hydration. In a hydration reaction, water is added across the carbon-carbon double bond of an alkene. During this process, the double bond breaks and a hydrogen atom and a hydroxyl group are added to the carbons. The result of a hydration reaction is an alcohol. One carbon gains a hydrogen atom and the other gains a hydroxyl group. This type of reaction is important because it shows how alkenes can be converted into molecules with functional groups that are common in biological systems. Hydration reactions are relevant in metabolism and biochemical pathways where enzymes help guide similar transformations under controlled conditions. Understanding hydration at the organic chemistry level provides a foundation for understanding these biological reactions later on. So to summarize, addition reactions occur when atoms add across the carbon-carbon double bond of an alkene. Hydrogenation adds hydrogen atoms and converts alkenes into alkanes, while hydration reactions add water and form alcohols. These reactions demonstrate how the presence of a double bond increases reactivity and allows organic molecules to be chemically transformed. Let's see if you can draw the products of hydrogenation in a hydration reaction by working questions 7 and 8 in Mastering Chemistry. One important thing to note in a hydration reaction, the hydroxyl group is going to add to the carbon that is more substituted or has less hydrogens associated with it. So here you're going to look at an internal carbon if the double bond is at the terminus, or a carbon that is going to be at a branch point. If both carbons in the hydration reaction or along the double bond are equivalent, you're going to get a mixture of both products. And I can work this out with us when we meet in class to talk more about predicting the products of different reactions. Now let's briefly introduce alkynes, the third major class of hydrocarbons that we're covering in this chapter. Alkynes are unsaturated hydrocarbons that contain at least one carbon-carbon triple bond. A triple bond consists of 3 shared pairs of electrons between 2 carbon atoms. Because of this, each carbon involved in the triple bond can only form one additional bond with another atom, usually hydrogen. Alkynes follow a general molecular formula where you're going to have n number of carbons and 2 times n minus 2 number of hydrogens, which reflects the fact that the triple bond further reduces the number of hydrogen atoms even more than the double bonds do. Alkynes are named using the suffix yne or -ine. For example, ethene contains 2 carbon atoms and 1 triple bond. Ethene is also commonly known as acetylene, FYI. And the carbon-carbon triple bond makes alkynes linear around the bonded atoms, meaning the atoms lie in a straight plane. This geometry is different from the tetrahedral shape seen in alkanes and the planar geometry around the double bonds of alkenes. Well, now let's move into a special and very important class of organic compounds called aromatic compounds. Aromatic compounds are based on the structure known as benzene, which behaves very differently from both alkanes and alkenes. Benzene is a 6-carbon ring with the molecular formula C6H6. At first glance, this formula looks unusual because benzene has far fewer hydrogen atoms than a saturated hydrocarbon with 6 carbons would normally have. This tells us benzene is highly unsaturated, but it does not behave like a typical alkene. In benzene, each carbon is bonded to 2 neighboring carbons and 1 hydrogen, forming a planar ring. The key feature of benzene is that the electrons involved in bonding are delocalized around the entire ring instead of alternating single and double bonds that behave independently. The electrons are shared evenly across all 6 carbon atoms. Because of this delocalization, benzene is unusually stable. The stability is what defines aromatic compounds and explains why benzene undergoes different types of reactions compared to alkenes. Rather than reacting easily through addition reactions, aromatic compounds tend to preserve the ring structure. Benzene is often represented using a hexagon with a circle inside. The circle represents the delocalized electrons shared across the ring. The shorthand is commonly used when drawing aromatic compounds and helps distinguish them from cycloalkanes that we saw before. Many biologically and medically important molecules contain benzene rings. And aromatic compounds are found in pharmaceuticals, hormones, vitamins, and neurotransmitters. Recognizing a benzene ring is an important skill in organic chemistry and in understanding how drugs are structured. When naming aromatic compounds, benzene is treated as the parent structure. If the benzene ring has one substituent attached, the compound is named by placing the substituent name in front of the word benzene. For example, a benzene ring with a methyl group attached is called methylbenzene. Some monosubstituted benzene compounds also have common names that are widely used, such as toluene for methylbenzene. When a benzene ring has 2 substituents, naming becomes more specific because the relative positions of the substituent matters. There are 2 common ways to name di-substituted benzene rings, using the IUPAC numbering or using prefixes ortho, meta, and para. In the IUPAC system, the carbon atoms in the benzene ring are numbered to give the substituents the lowest possible numbers. The positions of the substituents are then indicated using the numbers in the name. The ortho, meta, and para system is a shorthand method commonly used for benzene rings with 2 substituents. In this system, ortho indicates that the substituents are on adjacent carbons, meta indicates that the substituents are separated by 1 carbon, and para indicates that the substituents are opposite each other on the ring. Understanding how to recognize benzene rings and name substituted aromatic compounds is important because molecular position and shape influence how compounds interact in biological systems. Even small changes in the substitution patterns can lead to different biological effects. So to summarize, aromatic compounds are based on the benzene ring, which is unusually stable due to delocalized electrons. Benzenes can be substituted with 1 or more groups, and the positions of those substituents are described using either IUPAC numbering or the ortho, meta, and pairing naming system. To practice, let's see if you can draw an aromatic compound based on its name by completing question 9. When you're ready, come back. So to wrap up this lecture, let's walk through this summary and map together and connect the major ideas you've learned. At the center of this map are organic compounds. In chemistry, organic compounds are defined by the presence of carbon atoms. Carbon is unique because it forms 4 covalent bonds, which leads to a tetrahedral shape around each carbon atom. This bonding behavior is the foundation of organic chemistry. Because organic compounds are primarily made of carbon and hydrogen, they tend to be nonpolar. As a result, they will usually have low melting and boiling points, are insoluble in water, and are often flammable. These properties explain why many organic compounds behave differently from ionic or inorganic substances you've encountered before. Organic compounds can be represented in several ways. We have seen expanded structural formulas, condensed structural formulas, and line angle formulas. Each representation shows the same molecule, just emphasizing different features. Regardless of how they're drawn, organic compounds are named using the IUPAC system, which gives us a consistent way to communicate structure. On the right side of the map, we see the major classes of hydrocarbons. Alkanes contain only single bonds and are saturated. Alkenes contain at least one carbon-carbon double bond, and alkynes contain at least one triple bond. The presence of multiple bonds makes alkenes and alkynes more reactive than alkanes. Because of the double bond, alkenes can exist as cis-trans isomers, where the same atoms are arranged differently in space. These differences in shape can lead to different physical and biological properties, which is especially important in health and biological systems. Alkenes can also undergo addition reactions. In hydrogenation, hydrogen atoms are added across a double bond. In hydration, water is added across the double bond, forming an alcohol. These reactions show how unsaturated hydrocarbons can be chemically transformed into new molecules. Finally, we have aromatic compounds, which typically contain a benzene ring. Benzene is a unique, highly stable structure due to delocalized electrons, and it forms the basis of many biologically active and medically important molecules. Aromatic compounds are named based on the benzene ring and the position of any substituents attached to it. Taken together, this map shows how structure, bonding, naming, properties, and reactivity all connect. If you understand how carbon bonds and how hydrocarbons are classified, you have a strong foundation for everything that comes next in organic and biological chemistry. As you review this material, use the summary of this map as a guide to help organize your thinking and check your understanding before moving on. And again, in our next meeting, we are going to be doing our workshop where you're going to get a lot of practice naming alkenes, alkanes, and alkynes, both branched and unbranched, as well as benzenes. And we'll also get some practice in predicting the products from reactions involving alkenes. All right, so look forward to seeing you guys in class. Hope y'all have a great rest of your day.